Okay. If, welcome everyone to the first talk of CU Math seminar this semester. And today we have Erik Walsberg from University of California, Irvine, which I just realized that he just moved here. He have
A year
been,
ago, basically.
yeah. I still, I still thought that you were in Urbana-Champaign, but yeah,
Yeah. So until a year
yeah,
ago.
we have this talk, so I realized that you have moved back to California and live in sunny and warm weather now. Okay, and today Eric gonna talk about the etale open topology, and let's hear what he tell us. Okay.
Okay, yeah. So yeah, first of all, it's great to be able to give this talk. Of course, I would love to be there in person, but I also hate long plane flights, so okay. Pluses and minuses. But yeah, so all of this, just a few things before we get started. Everything I'm talking about is joint work with Will Johnson, with Chu Min Tran, and with Vincent Ye. And so, okay, just as kind of a disclaimer, first of all, this is not really connected to the etale topology from algebraic geometry, okay? Both of them are defined in terms of anatomorphisms, and there's some similarity in terms of the intuition behind it, but it's really something that's quite different, okay? So if you're hoping for some etale topology, yeah, you won't have it. Okay, and then just one other comment about how I'll start is that in my abstract, I say that we construct a topology on the k points of a variety over any field, for any field k. Now that is literally true, but it's sort of morally false, because this topology is sometimes discrete, in which case it doesn't really count. It's not interesting. But it turns out that the fields where this topology is non-discrete, that this is exactly some known interesting class of fields. It's what are called large fields. Okay, and I don't think that's a concept that's yet, extremely well known. So first, I'm going to talk some about large fields and about largeness before I, talk about the topology. So I'll spend a good chunk of the talk on that. Okay, so just notationally in this talk, K is always a field. I guess it's basically always going to be infinite as well. Okay, so first I give a definition of largeness, which is the usual definition that the field is large if whenever we have an irreducible curve over the field and it has a smooth K point, then it has infinitely many K points, right? This is the notation for the set of K points of the curve. Okay, now I know that probably not, okay, certainly not everyone watching is very familiar with algebraic geometry, so I will try to make this as accessible as possible. And on the next slide, I'll give a more elementary. Someone said something, and I'm not sure if it was a question or not.
I can fix that for you.
Okay. I mean, I also have the chat open if people want to use that to ask questions. So I'm happy to answer questions, of course. Yeah, but on the next slide, I'll give a more elementary version of this definition. Okay, that's a bit easier to understand. Okay, but first of all, I think this is not a definition that's initially like extremely natural. At least when I saw this, I don't look at this and say, okay, this is such a natural definition. So let me say something about where it comes from, because it comes from really pragmatic concerns. So this was introduced by Pop in the mid-90s. Okay, and he was interested in it for Galois theoretic reasons. He was interested in some Galois theoretic statement that I'm not going to state it because it's technical. But the point is, this is something that had been proven for various specific fields. And Pop realized that all of these fields were large and that this was the property that was really being used in the proofs. That's what you needed. Okay, and so in particular, he was able to use this to solve the inverse Galois problem over the field of rational functions with coefficients from a large field. So, okay, in particular, right, this means that he shows that any finite group can be realized as a Galois group over this field. Okay, and I think they've been studied probably most in Galois theory, but I think more and more they're being studied for other purposes. Okay, so before I give an example of a large field, I first want to give an example of, or some examples of fields that are not large, so we can see what we're not talking about. And so my first example of a not large field is the rationals. Okay, and so here we can give a very explicit example. Just take the curve that's given by this equation, x to the 4 plus y to the 4 equals 1. This is indeed a smooth curve. I have here a picture of the real points of the curve. Okay, it looks smooth, right? There's no singularities, right? And then it's a very, very, very old theorem of Fermat. Okay, I guess any theorem of Fermat is old, but right, Fermat shows that this curve has only 4 rational points. So, rational numbers, not large. Okay, now similar things work over some other fields. So for example, number fields are never large. Now here I attribute that to the Mordell conjecture, which is a theorem of Falting's. Maybe you can prove that with a bit less. That's a very deep tool, but I think this gives the nice conceptual reason, right? So, okay, I won't state it precisely, but roughly what the Mordell conjecture says is that if you have a typical curve over a number field K, it has only finitely many K points. Okay, so once you have something like this, it's pretty easy to get counterexamples to largeness. Okay, in fact, I think you can probably just take this equation and replace 4 by something bigger, but yeah. Okay, and there's some other fields where we have like some kind of Mordell conjecture. So for example, function fields, or specifically fields of rational functions, aren't large. Again, there's some, I think it's like Gerhardt-Mannens or something is the theorem. That's the Mordell conjecture over function fields. Okay, it's a bit more complicated, but again, it sort of says that typical curves have only finitely many points. Okay, now here I make a claim that's maybe a bit bold, which is that most other fields of interest are large. Certainly it's not true that all other fields are large. Certainly there are some examples of interest, but I think this is fair to say. Okay, or at least they're either large or we don't know if they're large or not. And large, you can take to mean, I like to think of it as anti-Mordellic. Okay, and I don't mean that like the Mordell conjecture fails, I mean like the opposite of the Mordell conjecture. So I think it's a very interesting observation that if you look at, again, not general fields, but fields that people are really interested in, most of them are either large or they satisfy some Mordell conjecture. I mean, certainly there are fields in between that one can cook up, but I don't think they're so interesting from what I've seen. And of course, just as a note, if you're a logician, right, like number fields, for example, are the kind of fields that model theorists can't say anything about because they're completely wild. They're like bi-interpretable with the integers. So if you're a number theorist, this is like the field you care about the most, but for us logicians, it's like, yeah, we weren't going to work with this anyway. Okay, so now I want to give some examples of large fields. My first one is just the real numbers. Okay, and I want to explain why the real numbers are large. So to do that, I'll give a more down-to-earth version of this definition, a more elementary definition. So a field is large if whenever we have an irreducible polynomial in 2 variables, and whenever you have a solution of the equation fxy equals 0 from the field, and if this second partial derivative is non-zero, then this equation has infinitely many solutions. Okay, so first let me say a word about why this is equivalent to our previous definition. Right, so the first definition was in terms of just irreducible curves. This is a statement about irreducible curves in the plane. This equation defines a plane curve. Okay, and you can reduce the statement about irreducible curves to plane curves because every curve is birationally equivalent to a plane curve. Okay. Okay, whatever that means, it just means you can reduce things down to plane curves. Now, what does this condition mean? Well, it means one, that the point is smooth, and two, that the tangent line is non-vertical. Now, the tangent line not being vertical, okay, that's not a major thing. If we have a plane curve with a smooth point, we can always like just apply some affine transformation to the plane to tilt the tangent line a bit. Okay, so that's a more elementary definition of largeness. Okay, so now why are the reals large? Because this is exactly a situation where we can imply the implicit function theorem.
Mhm.
That's why I make it so the tangent line's non-vertical, right? So we just hit this with implicit function theorem, and we get that if we have any point A prime that's close enough to A, there's a B prime, so that A prime, B prime is a point on this curve. So, you know, it sort of roughly speaking does look like this picture. Okay. So what did we need? We needed the implicit function theorem, but just for polynomials, right? Not for like general smooth functions. And it turns out there's a lot of fields where we have some kind of implicit function theorem. Okay, so one example is real closed fields. Okay, if you don't know what that means, the example to keep in mind is the field of real algebraic numbers. That's just the algebraic closure in Q inside of R. Okay, there's still an implicit function theorem there for polynomials. Then other examples come from Henselian valued fields. Okay, now again, this is something people may not know, so I don't want to define it. So if you don't know what this means, okay, it means a field with evaluation that satisfies Hensel's lemma. But what's more useful is to keep in mind some examples, because these are the kind of examples we actually care about, like the p-adics, also algebraic extensions of the p-adics, or fields of formal power series, like any field of Laurent or Puiseux series. And there's other kinds of generalized fields of formal power series as well. Okay, but again, in all of these, we have an implicit function theorem, at least for polynomials. Same proof works. Okay, so these are all what I call here topological examples, because the proof involves the topology, right? This sufficiently close, that's this topological statement over the real closed field. It's like the order topology. And then, you know, in the Henselian case, it's some valuation topology. So my next slide is going to be examples that are not where they aren't large for a topological reason, but for a number theoretic reason. Okay, now my first example is maybe mostly for logicians, which is pseudo-finite fields. Now, what are these? These are infinite models of the first order logical theory of finite fields. Okay, so I don't want to really try to explain logic in 2 minutes, but so what's the point? Is these are infinite fields that have the algebraic properties of sufficiently large finite fields. It's sort of like you take, you know, a field with p elements and sort of take the limit as p goes to infinity. Okay, in some way you can make this make sense and you get a pseudo-finite field. Okay, but what's the point? It's that at least certain kind of statements about pseudo-finite fields, what I very roughly call algebraic statements, are equivalent to statements about sufficiently large finite fields, so you can sort of translate back and forth. And that's why people care about these. And this has, you know, this has been useful for the study of finite fields. Okay, but I also want to give an example that's, okay, my next example is maybe more down to earth, which is infinite algebraic extensions of finite fields. Okay, so just one example, take a field with 2 elements. For each n, it has an extension with 2 to the n elements. These extensions will naturally form a chain. You take the union, you get an algebraic extension that's infinite. Okay, now also I just give this example here because this is not algebraically closed. So there's lots of examples of these that are not algebraically closed. Okay, I actually probably should put this in the slide, but algebraically closed fields are large. That's like easy to see. Okay, now in these 2 cases above, largeness follows from some fact about finite fields. It follows from the Hasse-Weil estimates. This is a special case of the long-Weil estimates, which are estimates for the number of points on a curve over a finite field. And again, I'm not going to state this, but in particular, you can use this to show that if you have a curve over a large finite field with a smooth point, then like as the finite field as the size increases, the number of points on that curve will go to infinity. Right? So that statement about like pseudo-finite fields, that's equivalent to some statement about like large finite fields having lots of points on curves. Yeah, and same thing works for these infinite algebraic extensions, because any infinite algebraic extension of a finite field can be written as a union of a chain of finite fields, and then you just prove things about the chain. Okay, so my third example is something that I think is sort of fun, which is, okay, Q bar as usual is an algebraic closure of Q. Take the Galois group here. Now this Galois group, this is a compact Hausdorff group in a canonical way. So in particular, it has a Haar measure. And okay, that Haar measure is unique up to rescaling, so there's going to be, by compactness, a unique Haar probability measure. So what does that mean, really? What that means is that there's like a canonical notion of a random element of this Galois group. That's really what this means. Okay, so once we have this, we can say, okay, pick like n elements of the Galois group at random, independently, look at their fixed field. With probability 1, that actually turns out to be large. In fact, fun fact, if you only pick one automorphism with probability 1, it's pseudo-finite. That's really a subject for an entirely different talk. Okay, and again, in fact, stronger things than largeness are known. A lot is known about these fields. Okay, and the proof again is number theoretic. I won't say anything about it because I haven't actually read the proof, but I looked at it for like 10 seconds and it seems to be using like some Chebytarev density type statement. Okay, another example that I just mentioned for those of you who know what it is the maximal totally real extension of Q is large. If you're a logician, this is an example of a pseudo-real closed field. They're all large. But I want to say a little more about a field that's conjecturally large, which is the maximal abelian extension of Q. Okay, which, the more elementary definition is that by Kronecker-Weber, it's the extension by all roots of unity. So this is, okay, I'm not sure if it's really a conjecture or a question, but it's open if this is large or not. And this would be significant. This would have very deep consequences. And it would imply a conjecture of Schaffer-Weivich on the absolute Galois group of this field, that it's a free profinite group. Okay, what does this mean? Okay, well, the point is that this would give you a description of this Galois group as a topological group up to isomorphism. So it would really tell you exactly what this group is, which would be, okay, that would give an important number of theoretical results. Okay, so the first examples were topological, where you had some topology, and these examples are like number theoretical. Okay, but what we claim in this project is that, in fact, these are also fundamentally topological objects, right? That there is some canonical topology on them, which at least to some extent behaves like the topology on the reals. So now I'm going to go towards defining this topology. Okay, so this is my little just, attempt to convince you that large fields are an interesting class. Okay, and if you're a logician, all known examples of logically tame fields are large. Okay, so everywhere in this talk, V and W are varieties over my fields. And again, you can basically think of this as something that's defined by a system of equations, of polynomial equations. Okay, so I need to say something about an etale-morphism. Okay, obviously it's in the title. I'm not going to define it because the definition, if you go look at the general definition, it's sort of hard and intimidating. But what I want to say is that in the case of a morphism between smooth varieties, this definition is much simpler. It's just a map that induces isomorphisms between tangent spaces. Right? So in differential geometry, this is the condition that ensures that you're a local diffeomorphism. So like etale maps, it's the algebraic version of a local diffeomorphism. Now, the general definition is harder because you have to deal with singular varieties and more general schemes and all sorts of things. Okay, so now I need to introduce this notion of an etale image. Okay, so if we have a morphism between two varieties, that induces a map from the k points of one to the k points of the other. If that morphism is etale, then we say that the image of that induced map is an etale image. Okay, so now let me give some examples to make this a little more concrete. Suppose we have a polynomial in one variable. That will be etale at a point if its derivative is non-zero at that point. That's all. So for one variable polynomials, very concrete condition. Okay, now this set of the condition of this derivative being non-zero that defines an open subvariety. So the image of that open subvariety is, well, the image of the k points of that open subvariety, that's an etale image. So even more concretely, the set of nth powers of non-zero nth powers is an etale image, at least as long as the characteristic of the field does not divide n, because that's the condition you need to ensure that the derivative of x to the n is non-zero away from the origin. Okay, so in characteristic 0, these are all etale images. So these are examples of things that will be open sets in our topology. Okay, so now I give some basic fact about etale images. They're closed under finite unions and intersections, and every Zariski open set is an etale image. Okay, for the proof, the only thing I say is that it's an easy consequence of standard facts about etale morphisms. You just like cite the right things from EGA. And this tells us that the etale open sets form a basis for a topology, and that this topology refines the Zariski topology. Okay, because every Zariski open set is an etale image, so it's a basic open set. Okay, so now that gives us a topology on the k points of each variety. But of course, we want to know how these topologies interact with each other, right? We want them to nicely play well together. So that's what the rest of these statements say. Like if you have a morphism, the induced map between k points is continuous in this topology. So like in particular, if you have like a one variable polynomial, it gives you a continuous map from the field to itself. If the map is etale, then in fact, this induced map if the morphism, I should say, is etale, the induced map is open. That's why we call it the etale open topology, because etale morphisms give you open maps, which is somehow like kind of similar, it's just kind of intuitive. Okay, and this last statement is about the situation where one variety is inside another. Like if you have like a curve in the plane, or a closed sub V is a closed subvariety of W. In this situation, there's two natural topologies on V of K. You can think about it as just intrinsically as a variety. It has its own etale open topology on the K points. Or you can think about it as a subspace of the K points of the bigger variety, and this induces down some topology. Okay, what this says is that these two things are the same topologies. Okay, I won't use that in this talk, but in practice, this is very, very useful. Okay, now one thing that's worth pointing out, this topology is often not a field topology. Okay, and that's very closely connected to the fact that the topology on products may not be the product topology. So if the etale open topology on K squared is the power of the etale open topology on K, you would get a field topology, but that doesn't happen in general. So for example, over pseudo-finite fields, this does not happen. Okay, I think we only proves it away from characteristic 2, but I'm sure it's true too. So I state some facts that are like a weak version of being a field topology. Like it's invariant under affine transformations. Any affine transformation gives you a homeomorphism from K to itself. And that serves as like a replacement for being a field topology. Okay, you know that, and you know that like polynomials are continuous, so that's almost as good as being a field topology. Okay. Yeah, and I do cover a lot of material so far, so do feel free to ask questions. Okay. So next I'll discuss the connection with largeness. Okay, so here's the result, that these three things are equivalent. The field is large, if and only if the topology on K is not discrete, if and only if the topology on the K points of any variety is not discrete, at least as long as it has infinitely many K points. Now let me just say a word about why that's necessary. we know it refines the Zariski topology. So it's T1, points are closed. So if our variety has only finitely many k points, it's going to be discrete. Okay, so let me just say something about why 1 and 2 are equivalent. Okay, I won't say anything about 3. But so again, I go back to the same picture of my irreducible polynomial with this non-singular point where the tangent line is non-vertical. And so now I let C be the curve defined by this equation. Right, that's just the plane curve defined by f of xy equals 0. And now the new thing in this picture is the projection from the curve to the line. That's a morphism. A1 is the line. Now this will be etale at a point if the point is non-singular and if the tangent line is non-vertical. Okay, that's what it means. Those two conditions define an open subvariety. So we restrict the projection to that open subvariety, which contains a B. We get an etale morphism. Okay, so now, suppose the field is not large. Then we can arrange things so that this field has only finitely many points. Then when we take the image of the k points of this open subvariety, we will get a non-empty finite open set. It's not empty because it contains A. Now that's enough for discreteness. Why? First of all, the topology is T1, so if you have a non-empty finite open set, you get an open singleton, and then it's invariant under translation, so if one singleton is open, then they all are. Okay, now for the other direction, use much of the same reasoning. If it's non-discrete, this etale image must be infinite, so the curve has infinitely many k points. Okay. So somehow, like, kind of part of the point here is some of these things that we get from the implicit function theorem, they're still true in this topology. Like if you have an A prime that's sufficiently close to A, there's a B prime so that A prime B prime is on the curve. Okay, except if the topology is discrete, sufficiently close means equal. Okay, so next I'm going to talk about some examples of what we actually get, right? So we have this topology that has nice properties in the abstract, but you want to know that, you know, in some cases you get something reasonable. Okay, so if the field is algebraically closed, more generally separably closed, we only get the Zariski topology. Okay. The point is here you can show that every etale image just is Zariski open. Okay, again, I won't say anything about the proof, but it's standard facts about etale morphisms. In particular, the fact that an etale morphism between schemes is open as a map between schemes. Oh yeah, and if you don't know what separably closed means, in characteristic 0, that's equivalent to algebraically closed, so you can just think about that. Okay, now in the second theorem, I'll say even less about the proof, but I just want to give some sense of what this is like, which is that if you aren't separably closed, or in characteristic 0, if you aren't algebraically closed, the topology on K is Hausdorff. Now that goes up to any projective variety or to any quasi-projective variety more generally, but we don't know about arbitrary varieties. We sort of realized, okay, there was some question in just a pure algebraic geometry that would have given a positive answer for arbitrary varieties. And I asked this on Math Overflow, and the impression I got is that people don't care about arbitrary varieties. But I would still like to know. Okay, so what this really also shows is, okay, over algebraically closed fields, we just get the Zariski topology, so we aren't really getting okay, it's not something new. So really, when we're doing something that's interesting is large and non-separably closed, like the examples I showed. Okay, so now what I want to say is I basically want to say that over large fields, over the topological examples of large fields, we recover the canonical topology. So if we have a real closed field, and again, if you don't know what that means, just think about the real numbers, the etale open topology, it agrees with the usual topology, the Euclidean topology. Over a Henselian valued field, okay, if you're not separably closed, because Henselian fields can be separably closed, then you just get the valuation topology. So like over the p-adics, algebraic extensions of the p-adics, formal power series fields, you get the valuation topology. Oh yeah, so I should have said, of course, if you put these two together, this covers any local field. Sorry, if you put these three together, this covers any local field that's not algebraically closed. And I was supposed to say back in the examples that all local fields are large. Like global fields are not large, local fields are large. Okay, so I want to say something about the proof of this over the reals, and then say a bit about how this goes up to the Henselian case. The real case is actually pretty easy, as you'll see. And then in the Henselian case, you just do the same thing, but you have to be a little more sophisticated. And in fact, there are even easier proofs than the one I give over R, but they don't go to the Henselian case. Okay, so first of all, over the reals, the implicit function theorem tells you that any etale image is open in the Euclidean topology. So that just means that etale open sets are Euclidean open. So Euclidean topology refines the etale open topology just from implicit function theorem. Okay, over in the Henselian case, you got to use like some algebraic version of the implicit function theorem. So I'll just talk about the other refinement on the reals, just why the etale open topology refines the standard topology, the Euclidean topology, and then to go up to arbitrary varieties, you just use some general argument that I won't get into. Okay, but I'm going to look at this polynomial x squared plus 1. That's etale away from 0. Why? Because the derivative only vanishes at 0. Okay. Yeah, so in fact, like most of what we do with it, a lot of what we actually have to do with anatomorphisms is like computing derivatives or Jacobins. Okay, so this image of this set, which is just the interval from 1 to infinity, that's an etale image. So it's etale open. And now what we're going to do is we're going to invert this. Okay, and to be clear, what I mean there is just we're inverting all of the elements. That gives us the 0, 1 interval. That's going to be open. Why? Because inversion is etale where it's defined. And again, you just compute the derivative. So that's etale over any field. So now we have this nice bounded open interval is etale open. Now we know that this topology is invariant under affine transformations. So the affine images of the 0, 1 interval are just going to be all open intervals. So they're all etale open, so same topology. Okay. Okay, so now in the Henselian case, we do the same thing, but we're a little more sophisticated. Okay. So, yeah, I'm going a bit fast. Okay, we do the same thing, but more sophisticated. Now, first we use the fact that we aren't separably closed. What's that mean? That gives us an irreducible, separable, non-constant polynomial. Okay, so x squared plus 1 is like the simplest example of such a polynomial over the reals. That's why I took it there. Now, what does separable give us? That gives us that the derivative is not constant 0, right? It's like, this in positive characteristic, non-constant polynomials can have constant derivative 0, right? Okay, but if we know that the derivative's not constant 0, then the set of points where the derivative does not vanish is cofinite, so we get a nice etale image. Okay, now what do we use irreducibility for? Well, what that means is that 0 is, there's no root. So 0 is not in this etale image. Okay, now in fact, we can use Henselianity to say that this etale image is bounded away from 0, just like what happened over the reals. So again, when we invert it, we're going to get a bounded set that's etale open for the same reason. Okay, now bounded here, I mean with respect to the valuation. Like being bounded means you're contained in a bowl. Okay, but if you aren't familiar with valuation theory, the point is that if you have a valued field, you have a notion of boundedness that really is very similar to your notion of boundedness over the reals. Okay. Okay, so we get a bounded set that's etale open. And okay, we can also show that this is open in the valuation topology. And now we look at its images under affine transformations, and we get a basis. So why is this a basis? Well, first of all, it's bounded. So when we rescale it, we can make it arbitrarily small. And then by translating, we get a basis. So it's intuitively, it's very similar to the reals. Okay, so what this tells us is that in many situations, we recapture some standard topology. So what that is this makes me think that, okay, this is something interesting, right? On other fields, the other examples, we get some new topology that we still don't understand very well, but we hope somehow that it's like a generalization of a Henselian topology. Excuse me. Okay. Yeah, so now I'm going to switch to a different topic for the last bit of my talk. So yeah, if you have any questions about this, let me know. But yeah, in particular, over any local field other than the complex numbers, you recover the usual topology. Okay. So now I'm going to talk a little bit about some Diophantine geometry. So I have this on its own slide because this is the title of the next slide. But as you'll see, I ran out of room on the next slide. And for the logicians who are watching, I'm really talking about existentially definable sets. But I'm going to phrase that in a way that's maybe more good to a general mathematician. Okay. So what does it mean for a subset to be Diophantine? Okay, what this means is that there's a polynomial f such that, so I have a subset of m-dimensional space over the field. And so a tuple a1 to am is going to be in X exactly if and only if, when we take this polynomial and plug in the a's for the first m variables, the resulting polynomial has a root in K. So it's like roughly, you can think of Diophantine sets as like sets of polynomials with roots. Okay, so these things have been studied quite a bit. So first I just state this. Okay, so this definition, originally I was gonna have a line that says let R be a commutative ring, but I ran out of space on the slide, so I just stated for fields. But of course this goes through for commutative rings. And then there's this very famous theorem, that's the solution of Hilbert's 10th problem, which is that any computably enumerable subset of ZM is Diophantine. Okay, so what this means is that if you have computably enumerable means that there's an algorithm or a program that can list the elements of this set. Okay, so the point is this covers like everything. Primes, powers of 2, Fibonacci numbers, palindromes, sums of primes and palindromes. Okay, so over the integers, Diophantine sets are incredibly complicated. Okay, so the rest of the examples I'm going to give are examples where Diophantine sets are somehow tame or somehow simple. So my first example is algebraically closed fields. Okay, you can think about just the complex numbers if you want. Now here, it turns out that a Diophantine set can be defined by a Boolean combination. So I mean, using, you start with these sets and then use Boolean operations finitely many times. Boolean combination of vanishing sets of polynomials and sets where polynomials don't vanish. Okay, now this first example, that's going to be Zariski closed. The second example is Zariski open. So if you do, okay, it's not totally trivial, but if you do a little work, you see that this means that the Diophantine set is a finite union of Zariski open subsets of Zariski closed sets. So like, if you're in like the plane, you could take like finitely many curves and then take like Zariski open subsets of those curves and then take the union. Okay, so these are some kind of sensible object from algebraic geometry. Okay, so I call this, I say this is Tarski-Chevalier. So Tarski was a logician. He proved some logical statement that has this as a special case. Chevalier was a geometer. He proved a geometric version of this that's very important in algebraic geometry. Okay, so now my next example is what happens over the reals. Now here it's a little bit more complicated. Again, it's Boolean combinations, again, of vanishing sets of polynomials together with sets where polynomials are positive, okay? In fact, it's easy to see that any such set is Diophantine. Okay, so I give the example here, you know, that we all know from childhood, which is if you look at the set of ABC, so that this quadratic polynomial has a solution in the reals, of course, that's the set of ABC where this polynomial equation is satisfied. Inequality is satisfied. Right? But the point is we do need an inequality there. Okay, now if you think about this set here, this is a union of two sets, right? The set where this discriminant is positive and the set where it's equal to 0. The set where it's positive, that's open in the Euclidean topology. It's not Zariski open, but it's Euclidean open. And the set where it equals 0 is Zariski closed. So this set is a union of a Euclidean open set and a Zariski closed set. And that happens, something like this happens in general. Again, a little argument shows that, you know, this kind of set is a finite union of Euclidean open subsets of Zariski closed sets. So now we need the Euclidean topology, right? So for example, even just the set of non-negative numbers, that's a Diophantine set, because it's the set of numbers that don't have roots, but that's not going to be of this, you know, type up here. Okay, so then lastly, I state the result over the p-adics. I attribute this to McIntyre, who proved a logical thing that implies this. I don't know if there was a geometric version before this. Okay, so one way of thinking about the result over the reals is that this kind of set here, where the polynomial is positive, that's almost the same as saying the set of A where f of A has a square root. Okay, you're saying non-zero square root, but close enough. Now over the p-adics, it's a little bit harder, but you just have to add in the set of A where f of A has an nth root for each n. Okay, so somehow for the reals, you just have to think about squares. Because, yeah, okay, for obvious reasons, you just have to think about squares, but then over the p-adics, you need to think about nth roots for all n. Now, this set is open in the valuation topology, basically because the set of the set, okay, this isn't quite open, but if we insisted that x is non-zero, it would be open. Yeah, because the set of non-zero nth power is open. But yeah, thanks, Atifat. I don't want to, yeah. But again, in a similar way as above, this will be the union of a valuation open set where it's a non-zero nth power and a Zariski closed set where it's just f of A is 0. Okay. It's a consequence of Hensel's lemma that non-zero nth powers are open. So again, it's a finite union of valuation open subsets of Zariski closed sets. So, you know, in each case, we get some reasonable geometric object, right? Like these kind of sets, you know, here, these are what we call semi-algebraic sets, and there's a whole beautiful theory of semi-algebraic sets over the real numbers. Okay, in the p-adics, that's also true, but maybe less developed. Okay, so now here's maybe the theorem that maybe you would guess at this point. Okay, but there's an extra condition. So this is our recent result. So if we have a field that is perfect, not perfect, I wrote this slide today because actually until yesterday, I thought I was giving this talk tomorrow because I got the date wrong. Anyway, okay, so if you have a field that's perfect and large, and if you have a Diophantine set, then it's a finite union of etale open subsets of Zariski closed sets. Okay, so we know that, you know, right, over algebraically closed fields, etale open topology is Zariski topology. Real closed fields, it's Euclidean topology. P-adics, it's valuation topology. So this result does generalize all of these. Okay, and in particular, it gives a uniform proof in the real and p-adic cases. Okay, so it shows that Diophantine objects are somehow well behaved. And so you can also think of this as saying that that they're finite unions of locally Zariski closed sets. Okay, so I just to say this, we're still writing the paper, so I am completely certain of the proof in characteristic 0 because it's not that hard. I'm very certain of the proof in positive characteristic, but it's possible that we made a mistake. I'm pretty certain it's true for perfect fields, but yeah, still need to read it a few more times. Okay, so first of all, just as some last few comments, I'm not really going to talk about most of what's on this slide, but this can fail when K is not perfect. We do need perfection. So if you aren't perfect, you have positive characteristic. So the example is when you're separably closed and not algebraically closed. Now, in that case, right, for separably closed fields, the etale open topology agrees with the Zariski topology. So our example is the set of Pth powers. That's a Diophantine set. And it's infinite, so it's Zariski dense, and it's co-infinite, so it's Zariski codense. Okay, so that's I think this is actually the only example we have, but at least I don't really know much about fields that aren't perfect, so. Okay, and then just maybe if there are algebraic geometers watching, just some kind of word about the proof of this. In characteristic 0, the tools are generic smoothness of dominant morphisms. That's the algebraic analog of Sard's theorem, together with the fact that if we have a smooth morphism, the induced map between K points is open in this topology. So that generalizes this fact about etale morphisms. So this proof in characteristic 0 is really not hard. It's really easy. In positive characteristic, we have to do more work. Okay, that's supposed to say CHAR. Okay. But just again, if there's algebraic geometers watching, right? Okay, the obstruction here is that a dominant morphism does not have to be generically smooth. For example, the Frobenius is not smooth because the derivative vanishes. But we can factor a dominant morphism into two things as where this is an iterate of the relative Frobenius, if you know what that is, and a morphism that is separable, by which I mean it induces a separable extension of function fields. Okay, maybe I should say all varieties in these lines are irreducible, and then it's generically smooth, and then you show that this relative Frobenius gives you a homeomorphism. But maybe just something maybe it's a little more useful I could say is that what's going on here is that, right, there's this fact from algebra where if you have a field extension, you can decompose it into a separable part and a purely inseparable part. And this is like a geometric version of that, right? A dominant morphism gives you an extension of function fields, and then this corresponds to this decomposition into, you know, the first part is purely inseparable, and then the second part is like separable. Okay, but yeah. Okay, so that's my talk. I just thought I'd say that we have this preprint on arXiv. So the stable field conjecture, that's logic, that's model theory, so I didn't talk about it. And so some parts of this paper are only comprehensible to model theorists, but most of it, okay, we tried, you know, to make it comprehensible to people who know some algebraic geometry. Okay, so that's all. Thank you.